So, good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Professor Georgios Kontogeorgis. Professor Kontogeorgis received a master's degree in chemical engineering from the Technical University of Athens, Greece, and a PhD degree from the Technical University of Denmark. Nowadays, he is employed at DTU as faculty member of the Department of Chemical and Biochemical Engineering. Among his several contributions, he is responsible for the development of the cubic plus association equation of states and has supervised over 35 PhD students and postdoctoral researchers. He is the author of over 220 peer-reviewed articles in international journals with close to 7,000 citations and over 250 conference contributions, oral talks, and meetings. He is also the author of several chapters in books and 4 books, the most recent ones on thermodynamics models for industrial applications, published in 2010, and on colloids and interfaces, published on 2016. Also, he has received awards from his research, including the Empiricon Award in Greece and the Dana Lim Award in Denmark. Professor Kontogeorgis' research and teaching interests are in the field of applied thermodynamics, environmental engineering, colloids, interfaces, and product design, as well as biotechnology. So once again, welcome Professor Georgios Kontogeorgis, and thank you so much for being here. And please feel free to start your presentation.
Thank you very much for the kind words. Let me see if I can share my presentation, and I will put it also in full mode. I think it can be seen, and I will start my presentation now. Thank you very much for the kind words. Thank you also very much for the introduction and the invitation to come again to this excellent seminar series. Today's talk will be about electrolyte thermodynamics, and I have to say from the very beginning that it is a teamwork from a very large team whom you see here, who are working together. So there are many colleagues, researchers, PhD students who are working together under the generous funding that we have received from the European Research Council, which is a foundation that provides funding for big projects in Europe. And the project that I'm going to talk about summarizes the work of all of those researchers. It started in 2019, and it will finish, we'll get some extension due to the COVID pandemic, it will finish in 2025. Currently, they are employed 9 PhD students and postdocs, and 3 have completed. And the overall target of the project is to obtain a fundamental understanding of electrolyte thermodynamics, not necessarily to develop new models, but if possible, to get some understanding of the thermodynamics of electrolyte solutions for a broad range of applications. I will start with some general thoughts about the topic, and then I will present the key questions in the project and the results that we have obtained. I will highlight some of the important results that we have obtained so far. Many of those questions are very much interconnected, and that's of course an issue with electrolytes, but I'll get into that in a moment. And there will be some conclusions and future studies at the end. Electrolyte thermodynamics is important, of course, in many applications, petroleum industry, chemical industry, biotechnology. So it's a very important topic. And I think John Prausnitz, a few years ago, in one of his books, he said that it is a science of its own, not just an extension of the non-electrolyte thermodynamics. So it is not a very easy topic, I would say. There are various views on the complexity of electrolytes, and both of those views that you see here, they are very much, I would say, they are both respected by me, and also in some way not as contradictory as it seems. My colleague and friend, the late Mikael Mikkelsen, used to say that life is too short to worry about electrolytes. And my other colleague, Kai Thompson, used to say that nature follows simplurus and maybe the most complex theory is not necessarily the best, it will be clear why both approaches have space in what it comes when we are talking about electrolytes. Starting from the latter approach, why sometimes even simpler models can be quite useful. I would say that the classical models for electrolyte solutions today are the activity coefficient models. These are the models that are being used in industrial practice. So the Pidgeot model, electrolyte and RTL, the OLI models, the extended uniquark are some of the highly successful electrolyte models. They are typically activity coefficient models. They require a lot of data for the parameter estimation, but they are very high. They are highly useful in many applications. They have been around for many years, and I dare to say that they may be around for another 50 years, if not for more. So these models are the state of the art today. And I have a couple of slides from the extended uniquark, which is one of those successful models. You can see a complex SLE diagram from calcium chloride water calculations done by Kai Thompson, and another one on the very complex systems containing ammonia, CO2, and water. So those type of models can actually perform very well in a wide range of cases. And they are the models that are mostly requested by industry, if we can start from this. In recent surveys that we have done about the industrial needs on thermodynamic and transport properties, that's a manuscript published last year, and also in a follow-up workshop that we did during the ESAT conference also last year, the models that were mostly requested by industry were the models that I just mentioned, the activity coefficient models. Maybe they were requested even too much, I would say. This recent survey, due to the dominance of one particular model, the electrolyte and RTL, in one of the commercial simulators, this is the model that has dominated in the request by industry. However, I have to say that today we are not going to talk about this type of models further, or about this type of, let's say, practical approaches. They are extremely useful. They have been, they are, and they will be very useful. But I hope that in the years to come, electrolyte equations of state and a better understanding of electrolyte thermodynamics could result in some maybe more fundamental approaches. And these are the type of approaches that I would like to discuss mostly today. And I have put them in terms of different questions, and in every question I will try to provide some answers and highlight some of the results that we have produced during the project. But please let me say again that all of those questions, I think I have around 10 questions and answers. They are very much interconnected. So this is of course a significant issue, sometimes a problem when it comes to electrolyte thermodynamics. The first question is, how do we develop an electrolyte equation of state? We need, of course, to add electrostatic contributions to a physical model, which could be a cubic or a shaft type equation of state. And the electrostatic contributions must at least include the ion-ion interactions, for example, from the Debye-Hückel or the mean spherical approximation, but there may be other terms, such as the Born term for ion charging. And there are important boundary conditions here. We don't have vapor pressure data for pure electrolytes. We need to go to mixtures to estimate the parameters of pure compounds. Electron neutrality is an important condition. And a debated topic is whether we have individual ion activity coefficients. So I'm going to get back into this topic a little bit later in the talk. So several of the members of our team, Martin, Nefeli, and Fufang, whom you see here, they are working on different versions of electrolyte equations of state. They use different physical terms. They use either the Debye-Hückel or the MSA equations for the ion-ion interaction and the Born term. But the theory is only part of the game, I would say. It's extremely important when we develop models for electrolyte solutions to recognize that the parameter estimation and the actual applications are at least as important. And this will become extremely clear from the results that I'm going to show. There are many such models, and that's why it's also very important to clarify a little bit the situation, because I started by saying that it is the activity coefficient models that dominate, but there are 60 electrolyte equations of state. Since maybe First and Renon and Donahue developed some of the first electrolyte equations of state already in the 20th century, there are very many such models having different contributions for the physical and the electrolyte terms and different ways to estimate the parameters. All of those models that you see in this slide, which is only some of them, they are in what I call the primitive approach, in which the solvent is a dielectric continuum. There are a few approaches under the non-primitive hat, which I'm not going to discuss very much today, especially the groups of Claire McCabe and Joachim Gross have worked into this. But this is not an approach which have attracted as much interest as it should, in my opinion, where all the interactions are being, let's say, considered explicitly. So most of the presentation today will be actually about the primitive approaches. So one of those approaches that we have worked in this project is the electrolyte Saft-VR-Mie model. So that's an electrolyte extension of the well-known Saft-VR-Mie equation of state. And you can see some very good results of the model without electrolytes for water hydrocarbons. And also for the eco-solubility of the hydrocarbon. And you can see for different hydrocarbons, a very good agreement also against experimental and simulation data. So this is a model that is quite good, and we have extended to electrolytes by using the Debye-Hückel and the Born term, and you can see some very good results from the work of Nefeli Novak for gas solubilities. And this type of systems require additional parameters for the ions with the gas. But even without any such parameters, there are cases, not all of them, but there are cases where we can get excellent prediction. In cases where we need even better results, we can get the parameters from the regression of the ion methane or the ion gas parameter experimental data. So these are some very good results with this model, and staying with the same model, but from another study that we published this year, you can see the density with this model that is very good if the density is included into the parameter estimation. So the dotted line that you see here is from the published version of the model when we have included the density into the parameter estimation. Now, in this work by Pierre Walker, we have compared the model in a predictive form as well, taking the diameter from different sources, but not from experimental data, and also using either mean spherical approximation or the Debye-Hückel theory. And what you can see here is that, first of all, if you don't include density data into the parameter estimation, the results are not good. It doesn't really matter which ion-ion theory you use. The second conclusion is that MSA or Debye-Hückel, the two ion-ion theories, perform equally well, or at least similarly. And the third, let's say, conclusion from this slide that will become more evident later is that the dielectric constant expression, the relative permittivity expression, can be very important in some of those calculations, even more important compared to which ion-ion theory we are using. This will become more clear a little bit later. The electrolyte CPA is another model that we have used, and when the parameters, when the density is included into the parameter estimation, we are able to get good densities, good activity coefficient, acceptable solubilities, SLE, and also very good densities at high pressures. So this is of course an advantage of the model, that the two lines that you see here are exactly the performance of the model when the density is included into the parameter estimation. The results that you see up here is when the density is not included into the parameter estimation. So you can see a very different performance, which is not necessarily only because of different theories. Here, actually, it's because of what type of data are included into the parameter estimation. We have extended the model. We have used also this model for gas solubilities for many different gases. You see the results here only for the CO2 solubility in multi-salt solutions. Now, those results are predictions. In those cases, the gas solubility is predicted. The gas salt parameter is obtained from ternary data, but these are data with multiple salt solutions. And we have a deviation of around 9% or so. And similar results we can obtain with the electrolyte Saft-Viarmé equation as well. There has been a lot of applications for activity coefficients, densities, and gas solubilities in electrolyte thermodynamics. There are much fewer applications when it comes to mixed salts, mixed solvents, and liquid-liquid equilibria. And I have to tell you that when it comes to liquid-liquid equilibria and mixed solvents is where we see maybe the frontiers of the models. For example, this is the system here with water, propanol, sodium chloride, and we have liquid-liquid equilibria, and particularly the composition of the salt in the organic phase is very poorly calculated. And this is not a random result. It's the same that we get here for water, butanol, potassium bromide. Even though there is a butanol potassium bromide interaction parameter obtained from the ternary system. So even though we have one parameter directly from those data, we cannot correctly predict all the types of phase behavior when we have mixed solvents and liquid-liquid equilibria. Again, the salt in the organic phase is a significant challenge. And we will get back into that on why this could be the reason. Now, the second, so this first question was, of course, a broader picture, the results. But many of the results illustrate that we have to go deeper into the model. And one of the models that we are using is the Debye-Hückel equation. So this is one of the models that we would like to go deeper. And the Debye-Hückel equation for us is much more than the limiting law or the extended law that you see here for the activity of an ion. These are simplified versions of the Debye-Hückel equation. They are valuable in certain applications, but they are simplified versions of the complete form, which is given for the electrostatic contribution to the Helmholtz energy here. This is the equation that is presented in the 1923 paper of Debye and Hückel. And this is the complete equation that has a single parameter alpha, which it is the distance of closest approach. For simplicity, I can call it the diameter of, or the solvated diameter of the ions involved. But, and then there is the salt concentration and the relative permittivity and the temperatures. They are all included into the thickness of the ionic cloud. This is the complete Debye-Hückel equation. And these simplified forms are obtained when, for example, the limiting law, we are ignoring the diameter completely. The extended law, we are assuming that all the diameters are constant. So these are simplified versions of the full equation. I have a little bit difficulty exactly because this full form exists. I have some difficulty in accepting statements in classical statistical mechanics textbooks that tell us, yes, we know that the full version exists, but please don't use it, because the model is rigorously obtained at the limiting law level. I have a problem in accepting this, at least when we are talking about engineering models, and I will get back into that. Jan Mollerup, I think, carefully read the original paper of Debye and Hückel and he presented in his book with Mikkelsen the complete form and the derivation that I have shown you. And the full version is back in the 21st century. We are using it in electrolyte CPA and in electrolyte SAFT-VRME. The group of Professor Sadowskis and Helt are using it in electrolyte PC-SAFT. And there are several other groups which are using the full version that I have shown you in this century in electrolyte equations of state. Now, an extra issue related to the Debye-Huckel equation is that the way Mikkelsen and Mollerup are deriving it, naturally a Born term for the ion charging is coming into the out of the derivation. And I will get back into this. What does it mean, this Born term, and how important it can be in the calculations? In the meantime, we have compared both previously and recently the mean spherical approximation and the Debye-Huckel equation, and we see that the results are very similar. And what we have noticed is that the crucial difference between the two approaches is not really the two approaches, is whether we are using a constant or a composition-dependent expression for the relative permittivity. We have done a parametric analysis, as you can see from this work from some years ago, but also this year, we have put both the MSA and the Debye-Huckel in the electrolyte SAFT-VRME in this publication, and you can see the results obtained in a predictive way for the activity coefficient. So the blue line is the Debye-Huckel, and the red is the MSA. This is a composition-dependent, and this is a composition-independent relative permittivity. So the effect of the relative permittivity is more important than the effect of whether we have one or the other ion-ion theory. And none of them is very good, as you see here in this version, compared to the literature versions from Selam and Eriksson, because these are predictive calculations where no energy interactions are fitted to the activity coefficient data. You also can see that if we need accurate activity coefficients, we need to fit some parameters to the experimental activity coefficient data. Now, the Born equation. The Born equation, for me, it's a mystery. It's the second most cited paper of Max Born, it's approaching 3,000 citations. It's a 3-page paper in German, published in 1920. And I have written a couple of years ago a 100-page review of this 3-page paper, which I decided not to submit for publication because I realized I understand so little about the Born equation. And let me explain what I mean by that. So it describes the hydration or the solvation, the ion-solvent interactions is this very simple equation. Here is in the form that we use in electrolyte equations of state. But there are so many questions for me, and that's this is why I have abandoned this paper for the time being. It contains the radius, the Born radius, which is probably not the same as the diameter that it should put in the ion-ion term. So which is the correct value for the Born radius? It contains a relative permittivity. Now, if this is independent of concentration, the Born term does not contribute to the activity coefficients. If it depends on the concentration, the Born term contributes very much to the activity coefficients. So which expression should we use for the relative permittivity? Moreover, the two parameters are together, also in the same part of the equations, so they may be extremely interrelated. Another question is this the correct expression for the ion dipole or for the solvation effects? So there are so many questions about the Born term, and some of those questions I will try at least not to answer today, but at least show you some results that indicate some answers. But I'm not sure we have the complete answers to those questions. We will get back into the Born term. So the fourth question, which is very much related to the Born and some of the previous, is exactly which relative permittivity should we be using in those type of models? because the relative permittivity of the dielectric constant depends on temperature, but it very much depends on the concentration. It decreases typically with the concentration. Should we include that into thermodynamic models for electrolytes? And if we should include that, which form of the dielectric constant should we include? Because it is presumably, it is assumed that there is both a thermodynamic and a kinetic part in this dielectric constant, in this composition dependence of the dielectric constant. So now, all of those things, the Born term, the ion-ion contributions, and the relative permittivity, the composition dependency, all of them together, they are combined into the next question: what is the balance of forces in electrolyte solutions? And now I'm going to show you 5 or 6 slides in which all of them, they look like this one to start with. They present with different models the contributions of the forces. And you will see the Born term goes up with increasing concentration, and you will see the ion-ion contribution going down with increasing concentration, no matter if the ion-ion comes from the Debye-Hückel or the mean spherical approximation. And you will see an activity coefficient that very often, with a successful model, goes via the minimum that we have sometimes with the experimental data, and it decreases first, goes via the minimum and increases. So we have a lot of models that show exactly this. This is from one of our studies, also here. It's exactly the same conclusions. From an earlier work from Jan Mollerup, which he noticed that, and he said, okay, that's the correct trend. Then from a work from the group of Jan Saltehem team, of their version of electrolyte CPA, here they are using the mean spherical approximation. It goes down, the Born term goes up. This is from a work of John Prausnitz back in 1991. The Born term goes up, the Debye-Hückel goes down. Not a very good scan, but at least you can see, I believe, the two trends. This is from electrolyte and RTL. Again, the Born and the Debye-Hückel are here. But, and now comes the but, if you don't have the Born term, or if you have the Born term with composition independent relative permittivity, are you doomed? Will the model fail? Not at all. Not at all. The physical forces, this is from the work of Nefeli with electrolyte shaft VR-Mie, the physical forces will counterbalance the Debye-Hückel or the MSA contributions. This is what we have seen with electrolyte shaft VR-Mie. This is what we have seen also with electrolyte CPA. Born Debye-Hückel, SRK Debye-Hückel. Isn't it funny or tragic, I would say, that we can't be sure even about the basics of what is the correct balance of forces at high concentrations? I think this is a very serious issue, especially when very different approaches can give equally successful results after the parameter estimation. With electrolyte shaft VR-Mie, the same thing from that recent study that I've mentioned to you. You can see Born, ion-ion, physical term, ion-ion interactions. In this case, we have a constant relative permittivity. In this case, we have a relative permittivity that depends on concentration, and this is why we have a Born term. To me, these are very important questions, and these are fundamental questions that, of course, have to be answered. Do we need the Born term? Do we need the composition dependency of the relative permittivity? Kai Thompson kindly has given me also this slide for the balance of forces in extended uniquark. And you can see here the Debye-Hückel and the physical terms. The extended uniquark does not have a Born term. So that's the contributions also in a successful activity coefficient model. Here you can see also the results of here you can see also, I would say, a conclusion that I have seen in a lot of studies by people that that work only on activity coefficient models, like the colleagues that I've mentioned here, Valisko and Boda and Silov and Lyasenko. So I have seen also statements that the activity coefficient composition dependency is a result of the balance between solvation and ion-ion correlations. This is, of course, very correct if you don't have the additional contributions. But if you have the additional contributions, they may have also an important role. So it's time for a change, writes Christoph held last year about the importance of the Born term, but the questions are still there, as I've told you. Nevertheless, the importance of the Born term was clear, even to Debye and especially to Erich Hückel. That's why Erich Hückel, 2 years after the Debye-Hückel paper, he published the Hückel equation that you see here. And in a work that is now under review from Gabriel, we have analyzed the Hückel equation, and in reality, the second term of the Hückel equation is a Born type term, and it demonstrates the importance of the composition dependence of the dielectric constant. But again, the Hückel equation has only those 2 terms and no physical forces. But where do we need the Born term? Where do we need the Born term in real applications? That's also a very important question. And I think from the engineering point of view, are there cases where we really need the Born term? And here I'm going to show you a few results from another work of Nefeli Novak and from a paper that we have submitted, and we are confident that it will be published soon. So the electrolyte SAFT-VR that we have been using had the Born term, but without composition dependency. We couldn't see any problem for ecosystems. Lithium bromide water, the results are very good. But when we went to non-ecos solvents, then even if we fitted the interaction parameter between the ions and the solvent, we were not able to represent the experimental data correctly. So we decided to look at various expressions for the relative permittivity. So in addition to the constant, which means no Born term, we looked at the mole fraction mixing rule, which Christoph Hell has used, and we looked also at the expression of Zuber et al., because this last expression is an example of an expression that represents the relative permittivity very accurately. While the mole fraction mixing rule, it shows a decreasing trend, but it does not represent the relative permittivity very accurately. Much to our surprise or to our sadness, or anyhow, this is life, or this is the conclusion, the correct results or the good results, we obtained them when we allowed for a weak dependency of the relative permittivity with concentration. This mixing rule that shows a weak dependency, which is not in agreement to the experimental data, we obtained excellent results with the electrolyte SAFT-VR for both ecos and non-eco solvents. I go back to the previous slide to see that this expression, unlike the Zuber et al. Expression, does not represent the experimental data, but it represents much more accurately the data for the activity coefficients. I don't know if we have to be happy or not happy. This is what engineering results have shown, and of course, this is an interesting conclusion that requires further thinking. But now, and I really need to spend, 5-6 minutes now on maybe the most important issue, because when we also see some trends like this, we have to go back to the Debye-Hückel theory, to the derivation, even to the full equation, in order to understand, are there things there that are a little bit tricky? And even this complete equation that you see here is obtained under a very serious assumption. Debye and Hückel arrived to the Poisson-Boltzmann equation, but in order to solve it analytically, they make the linearization assumption, and only using this assumption, they derive the full equation. The immediate question is, how accurate is the full equation compared to the non-linearized form if we solve it numerically? So this is a task that I was very happy that Gabriel Silva, one of our new PhD students in the project, took up this very serious challenge, and he compared the full Debye-Hückel with the numerical solution. Now the solid line is the numerical solution. The dashed line, the blue, is the full Debye-Hückel. This is the limiting law that is quite off, but the full Debye-Hückel is here. These points here are also the Debye-Hückel equation using constant diameters. You can see for 1,1 electrolytes, the difference, there is some difference in the linearization, but not enormous. As we go to more highly charged electrolytes, the linearization has a difference, especially at higher concentrations. That means that the complete Debye-Hückel equation may not be the perfect solution for charged electrolytes, and especially at high concentration. Something is missing. Maybe the ion-ion association, maybe the ion pairing that Niels Bjerrum has speculated so many years ago, back from the beginning of the 20th century, when he had his well-known fights with Van de Arrhenius about the electrostatic dissociation. So maybe the ion-ion association is an important aspect, and the ion pairing. And for this reason, in the PhD of Saman, we have decided to look at ion pairing somewhat in more detail. And one way to look at the ion pairing is to look at the electrical conductivity. This is a property that can depend on ion pairing quite significantly. And we looked very recently at the electrical conductivity with many theories. And you can see here the results. Again, of course, the Debye-Hückel limiting law is completely off. Here, there are various versions of the Debye-Hückel and the MSA equations. They are not very poor. They are not very poor. You can see them also here, but they are not perfect at high concentrations. So this is an additional indication that at high concentrations, we may be missing something. And we are not entirely sure what it could be. These studies are with constant relative permittivity. The results for more charged electrolytes, I would say, are even more problematic. So something may be missing for charged electrolytes at high concentration, and this could be the ion-ion association. We are currently investigating whether the composition dependency, the concentration dependency of the relative permittivity can provide a solution to this. We are in the beginning of this study. But there are more issues on the derivation of the Debye-Hückel equation. There are more issues. Gabriel has also worked on this, and the fact is that there are two charging approaches, or at least two charging approaches to develop the complete Debye-Hückel equation. The two equations that you see here highlighted are the full Debye-Hückel equation. They look very different, but actually in reality, for the mean ionic activity coefficients, they are identical. They are not identical for the individual ions, but if you write them for the mean ionic, they are identical. So there are, of course, some serious issues on the charging processes, because they are both derived under specific assumptions. And one important assumption that we have used, that is I would say included into this derivation is the fact that the composition dependency, if we include it after the charging process. Is that correct? Is it correct to include the composition dependency after the charging process? Silov and Lyasenko have tried to include the composition dependency before the charging process. And this is also something that we would like to compare. So my colleagues Xiaodong Liang and co-workers have looked at the approach of Silov and Lyasenko, who included the composition dependency before the charging process. They compare it to the full Debye-Hückel, where the composition dependency is included after the charging process. And they also compare to the extended Debye-Hückel equation, where we ignored somewhat artificially the derivatives of the relative permittivity. We were amazed to see that the Silov approach and the extended Debye-Hückel were actually identical. We were very surprised to see this, and we also concluded that the Born term is actually needed. That was a very, I would say, detailed study, and over 2 publications. We also concluded that the Silov and the extended Debye-Hückel approaches perform much better than the full approach, where we put the relative permittivity after the charging process. In everyday terms, I could say it looks like the composition dependency is too strong. Please remember the results of Nefelli-Novak that I have shown you before. So we also have a conclusion here that agrees with the previous conclusion. It looks like the composition dependency of the relative permittivity is too strong. And this is also something that we have seen from a study with electrolytes CPI. I'm taking the time a little bit, so I think I will skip this. But that was actually something that made us realize that we need to study that in very much detail. We need to compare where is the correct place to put the composition dependency of the relative permittivity, before or after the charging process. All the engineering equations of state, if they put it after the charging process. So we had to develop an approach before the charging process. And that's one of the most recent works of Gabriel. And it is just submitted. So I will, well, that's something to discuss a little bit at some other time on what will be the exciting conclusions of this work. I think time has flown. Let me go very briefly and mention the last 3 or 4 questions that I have only as a headline. Question number 7 is very important for me, because if electrolyte solutions have water as the basic element, can it be that we may see serious issues because we are not describing water very correctly? Can it be that the water structure is not accurately described? After all, water is a very strange liquid. It has anomalous properties, and none of our advanced association equation of states can describe several of these anomalous properties at the same time as phase equilibria. I have to tell you that over the last several decades, the two-state theory that has existed for 100 years, the two-state theory for water, has fascinated even more people, and it could be that it could provide an answer to the problem of structure of water. This we don't know for sure yet. It's something to be discussed. But what is for sure, what I can say for sure right now is that the experimental data for the monomer fraction. So this is the experimental, the low density liquid. So this is a function of this is the tetrahedral amount, the tetrahedral fraction of as calculated from equations of state, as calculated, as obtained experimentally from the data of Luke some years ago, and as obtained from the recent two-state theory. I knew that we were not obtaining good agreement with the data of Luke, and I hope that he was wrong. And I hope that new data will show that we are in this direction, and new data show that we are in the opposite direction. In a recent excellent work by Walter Chapman, they reproduced those data by some new parameters of PC shaft, but when you force PC shaft to reproduce those data, you lose the phase behavior. So something is wrong. Something is wrong with the description of water, and this is something that it needs to be, let's say, thought about. Molecular simulation can give us a lot of insights, and as part of this project, oh my God.
I'm going to talk what I have seen about other projects. Of course, I have no much deeper details, so Sheldon, feel free also to interrupt me if I say anything wrong. But actually, on the molecular simulation side, we have some projects in the ERC project that have dealt with this issue, and we have seen some interesting works also trying to get some interesting properties such as activity coefficients and especially individual ion activity coefficients, which is an issue that has been debated in the literature, but actually in some experiments and also molecular simulations, there are some heavy debates on whether these properties they are correctly or not measured. And there is something very interesting about them, which is in some electrolytes, when you compare for example, NaCl with with sodium fluoride, you see that the trends of individual activity coefficients between the cation and the anion, they get reversed. And this was studied by molecular simulations by Sina, which have somewhat shown some results about some discussion about these trends, and also on the importance of including dielectric constant to explain those results. Here is a table showing what I have just talked about between the trends of cation and ion when you compare them in the individual ion activity coefficients, because for some electrolytes, the results of the anion are below or upper when compared to the results of cations. And when using different theories, ECPA, MSA, or molecular simulations, you can get correct or wrong trends. Sorry, I don't know what he would say in this plot, but one thing that I find interesting is that we have some models that actually capture quite well the relative static permittivity of not only NaCl water, but many more other models. One of them is the Michael Michelson-Bryan model, which is somewhat more, it's more theoretical when compared to other models which are only experimentally. And also, when we change the relative static permittivity model, we are also allowed to change the trends of the individual ionic activity coefficients. So not only you can capture these different trends by changing the size of the ions, but also by changing the relative permittivity model you are using. So here's comparing capture a correct trend using ECPA, but just by changing the relative permittivity model. So when we use the ion association model for the relative permittivity, which is a model developed by Maritbo Mogensen, you can capture the correct trends of individual ionic activity coefficients. Here you can see that for sodium, the sodium results are higher than the chloride results. And only by using the ion association model, it was possible to capture the correct trend when comparing to the polyol and the salt-independent models. Here also the same result, of course, for ECPA. And in some cases, we have seen that it is not possible to correct these trends only by changing the size. You have to get a better relative permittivity model. From solids, we have now some projects that are actually dealing with quantum chemistry. And sorry, but I know nothing about quantum chemistry. I just know that there are projects which try to capture some properties using more fundamental ab initio calculations. And we have also some recent models, some recent projects that are starting now dealing with what machine learning can also be used for getting properties of electrolyte solutions, because we are also talking about many water or sometimes methanol, ethanol systems. But of course, when we get into biomolecules, there are very few works that deal with equations of state and try to get properties of these systems. So actually machine learning can help us in these systems that have sometimes fewer data and fewer models tested against them. Let's see. So I think he was going to end talking a little bit about Mikkel Mikkelsen, which has some strong opinions about electrolyte solutions. And some conclusions from all of this great amount of works we have is that there is some promise in using electrolyte equations of state, encouraging results, but of course, there is also a heavy debate on which type of physical terms, if you have to use Born terms, if we have to use hard sphere terms to describe all sorts of properties, because we have seen that even for an ACL, it is sometimes hard to find a model, a complete model, which can get the activity coefficients, osmotic coefficients, LCE, liquid-liquid equilibrium, right? The full de Baruchel equations and the MSA actually perform equally well for ion-ion interactions. And this is a very important point because sometimes we tend to think that the de Baruchel or the MSA, they should be used as complete models. But this is not a good point because they actually represent only ion-ion interactions. Of course, if you are going to represent more properties, we have to use other type of interactions between other models, such as ion pairing and bond term, which represent, of course, ion-solvent interactions. The parameter estimation is actually much more important when we are getting into representing equilibria of some systems, and this is a heavy issue because equations of state also have a problem for parameter estimation for non-electrolyte systems. And when we get electrolytes into the system, it gets much more complex, and the complexity of parameter estimation is also higher. The rule of concentration dependency of the relative permittivity, it allows for us to introduce the Born term into the modeling of activity coefficients, but there is still some debate in literature. Some people think that we should not use the Born term. Some other people advocate for the use of the Born term. But one thing is for certain is that the concentration dependency highly affects the outcome of many models. The mean ionic activity coefficients and osmotic coefficients, they are actually easier to compare to, for example, SLE or liquid-liquid equilibria to calculate and to get. And so you may have different models with different contributions, different parameters, and all of them can capture the activity coefficients and osmotic coefficients. But there is also a debate on how much physics you want to input into the model and which type of properties you want to represent. And also the individual ionic activity coefficients is a property that is not so well explored, but it can show us some difference, some physical difference between the models, because, for instance, we have seen that different charging process, they only give the different outcome when you compare individual ionic activity coefficients. They give equal mean ionic, but different individual ionic. So it should be a property explored to compare models. Also, we can get accurate density representation, but only in most approaches when you get the density inside the parameter estimation. Because when we are trying to estimate ion diameters, they do have a heavy influence in the outcome of practically all the models that we are using. We also need to better understand how to better represent water and all its anomalies. There are lots of ongoing projects on this issue. Also, thermal properties are much less studied, not only, I would add, sorry, not only with electrolyte equations of state, but also with activity coefficients model. And of course, for high temperatures and high concentrations, it is expected to have ion pairing effect, but this is not something much explored because we are still discussing low to middle concentrations, and we only expect to high concentrations to have ion pairing effects. But of course, we also have different ion pairing models, and we still have to try to understand which ion pairing models we need to use to represent this effect. For mixed solvents and liquid equilibria, we also have serious problems. Many authors do not use, for example, the Bohm term. They can get correct results through parameter estimation. And ion pairing is an issue that is less understood for water systems, and for non-aqueous and mixed solvent systems, it is somewhat much less studied. What is the influence of solvation? And of course, electrode conductivity studies and comparison of fluid barrique theory and complete Poisson-Boltzmann can indicate an importance of ion-ion association, because Bern, Fos, many authors in the literature have already stated that the missing piece sometimes can be ion-ion pairing, but this is something speculated, something that is not proven yet, something that is yet to be studied. Here, I think he would give very personal views. I agree, disagree with many of them. I'll leave that if he can join us. And we would like to thank, of course, the ERC project, which has funded many PhDs and postdocs projects, and it's still ongoing. We have lots of results yet to show. Thank you. On behalf of Georgios, I stopped the presentation, sorry.
Thank you, Gabriel. Professor Kontogeorgis is here with us again.
Sorry, I didn't know.
I thank you both for being here and for the presentation. We are now open to questions. If you want to ask one, please, you can enable your microphone, or you can write the questions on the chat and I'll read it. And our YouTube viewers can also ask questions by writing on the YouTube chat. Do we have any questions?
Hi, George. Can you hear us?
I think his image is like frozen.
Yeah. That I wonder.
Okay,
Uh-oh.
it's out again.
It's out again. Maybe Gabriel and
Okay. Here's here.
hi, George. Can you hear us?
Yes, I'm so really sorry. I mean, modern technology.
Yeah.
Okay. But I understand that Gabriel managed to at least you have heard maybe 45 minutes or so, but I think Gabriel managed to discuss the last 10 slides that I had.
Yes.
I tried to.
Because I when it crashed, it was when I was talking about the individual ion activity coefficients and how it gave us, let's say, the feeling that this has to be something that we should include in our studies. And in the work of Martin, it was we found that only by including the ion association, it was possible to represent also the individual ion activity coefficients. The other was the conclusions. So that's Gabriel. Thank you very much for taking over after this accident.
I ask you something. Are you thinking about include association in association ion water in this kind of model, GDSS model?
Fred, this is what we have done in the work of Martin, in the most recent work of Martin, which yes.
But association by like in SAFT, is it?
Yes. So that
Okay.
yeah, it is in SAFT. So we included. We assume sites in ions, and to include the ion-water association there, and the ion-ion association, and also in the work of Fufang, together with Jan Saltehemtin, we are including that in electrolyte PCSAFT, but it is at the very beginning, those studies.
But it's in equation of state. But how about in GGSS model, in liquid model?
You mean in activity coefficient models?
Yeah, but not like in a uniquark, unifork, or NRTL, TL, or so?
We have not done it, but I think Chao Chen, there has been a recent work on an extended version of electrolyte and RTL, including, I think, this
Yeah, he
contribution.
presented here.
He presented, okay.
Here.
Yeah.
It's very nice result. That because I'm asking you if you are thinking about it.
So we are only, let's say, in this project, we are only working on the equation of state, let's say, framework, Fred.
Okay.
Not on the activity coefficient, so we are not.
Okay. Okay. And in molecular simulation study, Thanos, as it's for individual ion, but it's a primitive model, or because
no, it's fully atomistic. Water is there completely.
But and you add the electric constant for that?
No. So
no. So
in the individual ion, there is no permittivity. It comes from the molecular model.
No, yeah,
you compute it directly. Yeah.
No, that I expect. So I understood wrong. Okay. Thank you.
Georgios, maybe I can ask a question.
Of course,
you can go ahead.
I have not seen too much in this presentation on, say, much higher temperatures, higher pressure systems that go away from sort of room temperature. Is that an area that would be of interest to industry and an area where you see these models being testable and able to do well also?
Yes, absolutely, Thanos. Higher temperatures we have done, not so much higher pressures with this type of models. It is challenging. Like I don't know if it is as challenging as the high concentration, but it is challenging. It will. It is not 100% certain that the ion-ion terms and the other contributions we have will work at the higher temperatures. Bjerrum effects, ion association may be important also at these conditions. It's certainly of importance to industry, also for weak electrolytes. If you go to CO2, ammonia, water, alkanolamines, all the applications related to CO2 capture storage that may include weak electrolytes and high pressures. So they are of importance. We haven't prioritized them very much right now, but they are certainly of importance to industry, certainly.
Thank you.
Does anyone have another question?
George, do you have results about interface property, like absorption or other kind of interface property, interface tension?
Fred, not with electrolytes, not with electrolytes.
Okay.
We have done interfacial properties for systems without electrolytes before, Xiaodong, Liang, and others, also from our group.
Yeah, I know, but
no electrolytes.
My question is, okay.
Your question was about electrolytes, I assume. Eh?
Yes.
No. We haven't looked into that.
And how about a water model? What kind of water model are you thinking include in this project?
Well, let's say the water model that we have included in those type of association models. We have included a four-site water model, both in SAFT and in CPA. We have not, with the existing parameters from the literature, so that's what you see with the results that you saw for electrolyte systems. We have not done other developments. In the parallel work that I showed very, very briefly, I demonstrated that the water model that we have has problems. We cannot represent the anomalous properties of water. and we accept that for the time being, and we proceed with that with the electrolytes. So that's, but we have not put an improved water model to develop a better model for electrolytes. So this we haven't done that, Fred.
Okay. Did you? I don't know if you had chance to see the Ken Deal presentation here in the seminar series. That he proposed some water model orientation that he can capture some of non-trivial properties of water. The problem is for vapor liquid equilibrium, it's terrible, but at least for some condensed phase water in high density, it gives some insight about the orientation of water, and change from orientation may give you some effect that can be interesting.
Of course, for me, Fred, at least for engineering applications, I would like a water model that can represent ideally the anomalous properties and phase equilibrium at the same time.
Yeah,
so
that's the problem.
We cannot sacrifice the liquid equilibrium with hydrocarbons in order to get the maximum of density. Or we should not get the maximum density for water at ordinary conditions and continue to have that also at all conditions. I mean, that was in a recent conference in UK, there was a nice presentation showing that there are some models that can capture some anomalous properties, but they continue to capture anomalous properties even when they don't exist for water. So we have to be consistent. So that's something that's there has been a review paper by Nesbeda recently. And so that's the presentation I'm referring from the recent conference. So we did some type of consistency that we capture the anomalous properties where they exist. And in the situation where water behaves as a normal liquid, we should also capture that, and also the water hydrocarbon or liquid equilibrium. And to me, this triangle that I just mentioned seems a challenge. But I'm open to listen to if there are models that can do that.
I don't know.
No, me neither. That's what I said. That.
No is the brief answer.
No is the brief answer, yes.
We have a question on the chat. Nicolas, would you like to ask, or do you want me to read it?
Yes, I can ask. Can you hear me?
Yes.
Can you open your camera, please?
Yes.
If you can.
Wait.
Oh, thank you. Nice.
Hi.
Hello.
Hi. My question goes for the work that you have done in soft equation of state. Would it be possible to obtain physically meaningful results using coarse-grained models for water? For example, those obtained by Olga Loganova in 2014, more or less?
Yes. The brief answer, Nicolas, the brief answer is I haven't studied them so well so that I can reply if it is possible or not. What I can say is that in the soft models that we have tested, and we have tested many soft models, we have not been able to find soft approaches that can represent both thermal anomalous properties and volumetric anomalous properties at the same time as phase equilibria. But whether this is possible with the approach that you've mentioned, this I don't know. So the brief answer is I don't know. The approaches that we have seen, the approaches that we have tried, I mean, we have not been able to do that. It has been notoriously difficult to do that. And we are also not 100% sure which is the optimum objective function for water in this type of soft models. I mean, which properties should we include together with which theory in order to represent some of those properties? I have noticed that several soft models can represent the minimum of the heat capacity if heat capacity data are included in the parameter estimation, but not the maximum of the density. So not the volumetric anomalous properties are more difficult. But yeah, that's my observations.
Yeah, okay. Yeah, because I noticed in Olga's work, she had like 5 different models because there's not a unique parameterization for coarse grain models for every property. So,
but I will check it out a little bit now since that you mentioned, because I haven't studied maybe as carefully as I should. This one.
yeah, maybe because molecular orientation is so important in this phenomena, maybe coarse grain models are not the best.
Yes, but yeah, I can't be sure at which level of details you have to go in order to represent all the properties. Yes, this is what I'm sure.
Okay, thank you, Professor.
We have another question on the chat rule. Would you like to ask, or do you want me to read it?
Yes, I can't. I don't have a camera, sorry.
Okay, no problem.
No problem.
Professor, as you say, the electric constant is very important, but the ions don't have a dipole moment in order to calculate the electric constant using the dipole moment. And so depend of the model of the water. In this case, when you use molecular dynamics, using this idea, using the correct water model that can reproduce it is a first step to calculate the properties with water and ions, right?
But I would say, I'm not sure I understood all the aspects of your question, but I would say the dielectric constant, the relative permittivity composition dependency that we are using is an input in those type of primitive models, I mean, for the equations of state. So we are using equations either from experimental data or from mixing rules like the ones I have shown. So it is, or from other theories. So these are theories, equations, or correlations from the literature that we are using for the composition dependency of the relative permittivity. So that's so at least in the equations of states, this is what we are doing. I think I don't know if Thanos is at all around, but I mean, I think in the molecular simulation work is of course.
I am, yeah.
I don't know if the
Yes.
question, Thanos, was also for the molecular simulation part, but there it's an output, I guess, the dielectric constant, not an input.
Yeah, for the simulations, it is very important to have that the model has the right dielectric permittivity, the model for water, and that we have checked that the concentration dependence is correct, and it is. So,
yes.
Okay.
Unfortunately, I have to go. I have another meeting. So thanks a lot for every.
Thanks, Thanos. Thank you.
Thank you.
I don't think we have any more questions, right? And our time is almost up, so we're headed to the final announcement. I would like to thank you so much, Professor, for being here with us today and for the lecture. We're going to share some slides now. I would like to remind you all that our seminars are being recorded and posted on YouTube. You can check them out later. Next slide. This is our seminar committee. We are responsible for communicating with the lecturers and handling social media and hosting the seminar. So this is our team. And our next seminar will be 2 weeks from now. Professor Tim Kruger will be here with us. So I hope to see you all here for his seminar. Thank you all so much for being here, and I see you all 2 weeks from now.